That would help.
So let's, do you guys, I've got all the solutions, right? Okay. Sorry for the change in format. Apparently, the thing is, I have the assessment day on all my other course planners. Just somehow I missed it on yours. So sorry about that. So for that reason, like Math Battle 3 is obviously like truncated, right? So let's just talk about it. So I just handed you back quizzes 7 and 8, and I should enter the grades for quiz 6, but I haven't done that yet. So I must have a sheet in my folder somewhere. I'll find it. If I don't find it, everybody's got a perfect score, so hooray. So let's see here. So I was going to say some things, like just because you have a high score on the last two quizzes doesn't mean that you understand. I've been very generous. Like basically if you've taken the quizzes and done something within the realm of plausible logic, I gave you a lot of points, but that doesn't mean that I'm going to be similarly generous on the test. Like I do need to see limiting notation for one thing. Like I didn't take points off anybody for not writing limits, but there are many who are not writing proper limit notation. What's proper limit notation? Well, the notation I always use. All right, so like you won't see me writing something without a limit where the limit's supposed to be, right? So that means something. It's a technical operation that we defined in terms of epsilons and deltas and junk, and you know, writing that limit symbol says a lot that you don't want to have to say in sentences. It's a compact notation for a precise mathematical notion. So you need that limit notation where it should be. That's one thing. The other thing is I just see category errors. Like you're trying to do indeterminate power stuff on something that's just like a, 0 times infinity or infinity over infinity or something like that. You're bringing to bear the exponential and the natural log, but it's not even an indeterminate power. So like, what are you doing? I mean, you're just doing what I was doing right before the quiz, right? Which was indeterminate powers. But the thing is, the quiz didn't have that wasn't an indeterminate power problem. I see a lot of people doing that. So I think you'll get that out of your system by Thursday. I mean, I really hope. So you need to settle in your mind, like, there's different problem types, right? Like you do infinity over infinity or 0 over 0 or 0 times infinity in a very different fashion than you do the 0 to the 0 or the 1 to the infinity or the infinity to the 0 type indeterminate powers, right? They require a different approach. So beware of that. The other thing is situational awareness. Like you need to know the closed set test, right? Closed set test is very simple, but it does mean things like, so you notice here for like problem 1, I found that we had critical numbers 0 and 2, right? And then I said, apply the closed set test, right? F is continuous on the closed set 0 to 4, closed interval, right? And so I just check f of 0, f of 2, f of 4. I get 7, 3, and 23 respective, right? So my minimum's at 2, obviously, and the maximum's at 4. I do not need to then do the second derivative test. So some of you are doing that. Now, the second derivative test wouldn't cost you much here, right? This example, differentiate again, no one's going to break a sweat, right? Like, easy. But like that problem on the quiz that I had, e to the minus sine squared, if you calculated the second derivative of that took you some mental energy, didn't it? And you didn't need to, see, because we'll get back to that, but the quiz problem, it was a closed set test. It was from -1 to 1. So all you had to do was find the critical numbers between -1 and 1 and check the endpoints, right? So know the closed set test, know what it says, know what it doesn't say. So you don't have to check whether or not you've got maximums or minimums. You don't have to use the first or second derivative test. If you're using the closed set test, it's an end unto itself. All right? Because it gives you the global extrema for the continuous function on the closed set. Simple as that. So that's one thing. But I hope you guys got this problem. I bet you guys got this one. Should I look? I mean, I'm not going to look. I'll be surprised later. Problem 2. There's strength in numbers. So you guys got all these right? So limit is x squared plus x over e to the x goes to infinity. This is just a plain old garden variety L'Hopital's problem, right? Infinity over infinity, L'Hopital. Differentiate the top, I get 2x plus 1. The bottom, I get e to the x. Then still infinity over infinity, so I L'Hopital again. And then I get to 2 over e to the x, which clearly limits to 0. All right? End of story. I hope you guys got that one. The next one, what might stop you on the test is if you don't know what cosecant is. But you're supposed to know what cosecant is, right? Cosecant is 1 over sine. So this is literally sine ax over sine bx, which as x goes to 0, you got sine of 0, sine of 0. You shouldn't need to pick up a calculator. By now, we've said it like 100 times in here. You should know sine of 0 is 0, right? And cosine of 0 is 1. So after we apply L'Hopital's rule here, we're free and clear because we've got a cosine, b cosine, right? And if I plug in 0, I just get a over b. So the answer is a over b. By the way, there are slightly harder examples than the math battle has covered, right? On the test, you have 75 minutes. There's a certain like harder kind of question I might ask there. Like I did something involving square roots and negative numbers. I wouldn't be too surprised if that came up on the test, for example. Anyway, you guys can ask me more if you want. Problem 3, this is a novel question. It's a question I just invented, so you know, but I hope some of you answered it, maybe. If you didn't, it's understandable, because this is, you know, a little bit different. But the point here is if you have inflection points, what are those? Those are places where the concavity changes. If concavity changes, it either has to go plus to minus or minus to plus. So logically speaking, if minus 2 and 3 are the only places where you have the concavity changing, it forces you either to have the pattern plus plus minus minus plus plus or minus minus plus plus minus minus, right? But then if I have critical points, as is given, right? Because I gave you f prime of minus 5 and f prime of 5 are both 0. That makes minus 5 and 5 critical numbers. So that's where the second derivative test applies. And so the second derivative test says that either they're both local mins or they're both local maxes. That's how the their fate is shared. So, you know, if you didn't get it, no shame, but now you know the kind of thinking that you can do for that kind of problem, right? You basically want to think about the theorems that we have, which are what? First derivative test, second derivative test, like definition of inflection point, definition of critical number, and think about how those work together, right? You should, you know, review, of course, like Rolle's theorem, mean value theorem, Fermat's theorem. These are all important for the test Thursday. Let's see here. What else? Okay, so now this problem 4, similar style to like problem 3 on the quiz that a lot of you opted out of because it had more stuff to do. That's fine. I told you to pick 2, right? So here I differentiate, and I got to do the product rule, and I got to do the chain rule, and the chain rule makes that a minus x. See, because I get minus 2x over 2, which is just minus x. So x times minus x is minus x squared. I factor out the exponential, and then I factor this 1 plus x, 1 minus x, right? Which either gives me 1 or minus 1 for my critical numbers. Then I differentiate again to find the second derivative. The derivative of this is minus 2x, and then I've got 1 minus x squared to the exponential times the derivative of the inside function, which we just worked out was minus x. So if I haven't made a mistake here, hopefully, I get x times minus x is x cubed, and then I've got a minus x from here and another 2 of them from here, so that's a total of 3. So I get x times x cubed minus 3x, which factors to x times x plus root 3 times x minus root 3, which reveals to me that the zeros of the second derivative, which are the possible points of inflection, it's where the possible points of inflection are at. It's annoying. We don't really have a name for the x value of an inflection point. There's some professor somewhere whose students has named them after him just to give them a name, but I forget it, so it didn't really stick. Anyway, like they're like Hurwitz numbers or something silly, but that is not widely accepted. But that professor's students have made up shirts with like that professor's numbers because it's like a pet peeve of him that they're not named. So I think the students named them after him, and they made T-shirts up and stuff. It's very exciting. But anyway, so we got 0, plus or minus 3 are my possible points of inflection. In fact, they actually are points of inflection where those are, because the second derivative changes sign from plus to minus or minus to plus as we go from left to right at the number line of f prime prime. So then I take everything I have, I draw my sign chart for f prime, my sign chart for f prime prime. I make a mistake and I put the wrong things, I get my whiteout, I fix it. And how did I fix it? Well, I fixed it because I know that 1 and minus 1 are critical numbers, right? And I was convinced that I've got minus here, but my previous pattern was minus to plus. Well, the first derivative test would tell me I've got a local min. But the second derivative test would tell me I've got a local max. Well, I can't have both, so I got an error. And then I went back and I looked at my first derivative and I realized, oh, it's negative for large values of x. I'm a dummy. So then I whited it out and fixed it. Minuses are easier to change to pluses, so there's no whiteout in the middle. But anyway, there's some irrelevant details. So there's my sign charts. I can see where it's increasing, where it's decreasing, where it's concave up, where it's concave down, right? It's decreasing from minus infinity to minus 1 and from 1 to infinity. It's increasing from minus 1 to 1. Concave down from minus infinity to minus root 3, also 0 to root 3, and it's concave up from minus root 3 to 0 and from root 3 to infinity, right? Where the second derivative is positive, concave up. Where the second derivative is negative, concave down. By the way, if you use L'Hopital's rule, you can, and this wasn't asked for, but this would have been a good follow-up on my part, right? This would have been a good, I should have done this. I should have had like a part D, which is to calculate the limit at plus or minus infinity of x e to the minus x squared, because that's a great moderate L'Hopital problem, you know? Because that's x over e to the x squared over 2. Take that minus, bring it downstairs, makes it a plus, right? And then that's infinity over infinity, L'Hopital that thing. And then it's just 1 over something huge, which limits to 0. That's to say that there's horizontal asymptotes for this graph going both ways, plus and minus infinity. So I can expect that. My graph is going to get drawn into the x-axis long term. We got this point of inflection here, and here, and here. Concave down, concave up, concave down, concave up. Decreasing, increasing, decreasing, max, min, and there's just a 0. There's just 1 0 for the function. I deleted this. Originally there's a part A that asks you to find the zeros of the function, but I thought that's just kind of like cluttering the problem, so I got rid of part A for this. But on the quiz there was also find the zeros of the function, which would be like, you know, make a sign chart for the function itself. That's what we do in pre-calculus, right? Pre-calculus, we just make the sign chart for the function, because we don't know about derivatives in pre-calculus, because it's pre-calculus, right? So, any questions? Do you guys feel like with another, day of studying and half day of sleeping, you got a chance doing these on Thursday? All right. I hope so. I have enough of your points. I do not want any more of them. So, here's the quiz 7. Take a walk back down memory lane here. So to start with, we got ourselves a critical number of either 0 or 2/3, all right? And then I draw my sign chart. Take a point off my solution. I really should have df dx here, right? You should label your sign charts. Let me know what I'm looking at. Is this the sign chart for the function? Is it the sign chart for the derivative? Like, what is this? I'm missing a label. My bad. But with that in mind, we're going minus to plus. That makes this a local min. Plus to minus, up and then down, that's a local max. So local min, local max. Technically speaking, the value of the function is the minimum or the maximum. X where it happens is where it happens at. But my brother says that if you take points off Calculus 1 students for like you know, like this, you're like, somebody here says, oh, x equals 2/3 is the maximum. And then the instructor's like, no, incorrect. 4/9 e squared is the maximum. It happens at 2/3. My brother says that if you're a Calculus 1 instructor, you take points off for that, you're just being a jerk. So I don't want to be a jerk, so I don't take points off for that. But logically speaking, the maximum is the output, right? And it's happening at 2/3. But I just don't police the language there because, as I said, I've taken too many of your points already. But there is a conceptual, there's a conceptual point to make there. There's a difference between the x and the y, right? All right, this is the problem I was talking about a minute ago about the closed set test. This is a closed set. If you're asked to maximize and minimize something on a closed interval, you're probably supposed to be using the closed set test, also known as the extreme value theorem. So yeah, so I calculate the derivative, and listen, if you use the trig identity to switch 2 sine cosine to sine 2x, great. If you don't, you could still just look for where is sine or cosine 0, right? Where is sine or cosine 0 from -1 to 1? You should be able to figure that out, right? Sine is 0 at 0. It's also 0 at plus or minus pi. Plus or minus pi are like 3.14 plus or minus, right? That's outside the scope. So you got 0 is where sine is 0. Where's cosine 0? Well, cosine is 0 at plus or minus pi over 2. Pi over 2 is what? Like 1.57. It's too big, right? They did something wrong. They did something very wrong. Watch this. Oh well, thought I might get something in back. If I knew Morse code, oh well. I never got into ham operator. That Morse code thing just soured me on it. But anyway, I digress. So the point is that the only critical number here is where sine is 0 at 0. The rest of them are outside of the realm of consideration here because we're looking at -1 to 1, right? So there's just one critical number, 0, and we have to check the endpoints, -1 and 1. It just so happens that the function here is even, so like -1 and 1, they share the same fate. They both go to 0.4311 approximately speaking, so there's your maximum, and here's your minimum, which is attained at both of the endpoints of the interval. And that's it. By the closed set test, you're done. You don't have to use this first derivative test. You can't even use the first derivative test because it's outside the scope. And 1 and -1 aren't local mins and local maxes in the sense of the extension of the function past the closed interval. Are -1 and 1 local maxes with respect to the closed interval? I would say yes. But anyway, different calculus books might disagree with me on that. So here is problem 3 on quiz 7. And here you had this quartic function. You're supposed to find the x-intercepts, also known as the zeros of the function, critical numbers, possible points of inflection. Well, these are actually inflection points, intervals of increase, and the intervals where it's concave down. All right. So, yeah, and sketch the graph. So here's what I did. To find, there's lots of algebra in this problem. I like this problem. Lots of algebra. So first of all, I factored out an x squared because you can. And then with that in mind, I completed the square on the quadratic because we can always do that. And so doing reveals that the x-intercepts are at 0 and 2 plus or minus root 12, which you could also say is 2 plus or minus 2 root 3, because 12 is 4 times 3 and the square root of 4 is 2, and so you could look like that. Okay, fine. And that's fine. So that the x-intercepts from factoring the function directly. Critical numbers. So this is just pre-calculus. Okay? But it's pre-calculus that most of you need to practice. Yeah? So df dx, 4x squared, 4x cubed minus 12x squared minus 16x. I just differentiated the function as given. And there's a common x. There's a common 4. Pull it out, right? Factor the 4x out, and then you got this. Oh, but that's just plain old garden variety factoring, right? just plain old guess and check factoring. So x minus 4 to x plus 1. Critical numbers, 0, 4, and minus 1. A lot of you got that. And I'm very happy to see that. That's great. That is actually like the first thing. So that's really good. You got that, if you got that. Then I differentiate again, f prime prime. That will show me where my inflection points could be. Differentiating gives me this quadratic. I can factor 12 out of that. I do that because I like to complete the square with the coefficient of x being 1. Then I complete the square. I've got x minus 1 quantity squared. I have to subtract 1 from 16 twelfths, which is to say subtract 12 twelfths from 16 twelfths, which gives me 28 twelfths. And then I simplified that to 7 thirds. And so at that point I can see that the zeros are 1 plus or minus root 7 over 3. And some of you wrote that a different way. Like some of you had like a huge number and another huge number and square roots and junk. And I'm like, huh? And I got my handy dandy calculator out and I punched it in. And then I subtracted the square root of 7 over 3 from it. And I got 0. I was like, oh, okay, we agree. So, yay. So your number could look very different than this, but still be the same. Anyway, so that works out to about minus 0.53 and 2.52 for my inflection points. And so part D, here's my sign chart going back to critical numbers, minus 1, 0, 4. So you can see it's increasing from minus 1 to 0 and also from 4 to infinity. So that answers that question. And there's the sign chart for the second derivative. So you can see it's concave down from here to here. That answers that question. And then put it all together, I've got zeros at 0 and here. So I went back to the starting point and I plugged in, like I found some decimal numbers for the zeros just so I could try to make it somewhat accurate. And then of course the y scale is not to scale, right? I try to focus more on the x being accurate, but the y is never quite like legit. It's not the same scale as the x for sure. Okay, so minus 1 was a local min, 4 was a local min, 0 was a local max, and it's like concave up here. It's concave, it's concave up here. It's concave down from there, and it's concave up again over here. So those are the features that you'd like to have on the graph. And you'd probably like to make the graph bigger than I made it, but you know, sorry. Poor planning on my part. I should have left myself more room for the graph, all right? If you ever feel like constricted and you don't have enough room to make the graph, turn the page over, say graph on backside. I always print tests single-sided, so if you need to put more work, you can put it on the back of the page. It's not a big deal. Just warn me that you did it so I don't miss it when I'm grading, okay? Let's see here, what else? So you guys got any questions, you can jump in. Let's see here, what other quizzes have we had? Did we look at the L'Hopital quiz solution yet? I don't think we did. So here's the quiz you guys took yesterday. So I had a token. So the other kind of maximization problem, minimization problem, make sure you review is like find the closest point on a graph to a given point. Those are good test questions. All right, they're pretty easy to set up. We had problems like it in the homework. I did examples in class. You know, we found like the closest point on a line to a point off the line. And I think we also found the closest point on a parabola to a point off the parabola. There's a variety of questions like that I've asked on tests before if you look back. I have to be careful. It's easy to make one of those max-min problems be very, very intricate, and I don't want it to be too hard either. So here I realized that I had to add 5 mid-quiz because otherwise the minimum cost would be negative, and I don't know. I'm not an what's the word? Economist. Yeah, I'm not sure what negative cost means. Although I do feel like I should just buy goods right now. Like I should just go like take money in my bank, and I should just go like buy large machinery and like sit it in my basement so that my money doesn't like just poof in the year, you know? Like, because Biden said we had 3% inflation in the State of the Union address. That's crazy. Have you been to the grocery store? Like, it is so much higher than that. Every time I go back to the grocery store, I feel like chips have gone up another $1. I don't even like chips, but you know, I mean, like, it's like $5.50 for a bag of chips. They're $2.50 like a second ago. And now gas is back up to $3.50, but that's cheap because the inflation, actually. So if, like, I don't know, how do you feel about that? Like, yeah, the gas is more expensive, but it's not really, see, because money's not worth as much now. So is the gas really that expensive? I don't know. But anyway, I shut up. So x equals to 1 is the critical number here. There are two others, -1 and 0. But those are not reasonable times, right? So for physical reasons, we reject 0 and -1 as critical numbers here. 1 is really the only one. And just as a double check, here's my second derivative. As you can see, it's positive, which means it is indeed a local minimum. So in fact, it's the global minimum given context here. So that's the minimum cost is with making them in 1 hour. That's your best bet if you're making widgets. I apologize that my word problem was not as interesting as it might be. Like, I feel like I have missed an opportunity to make some horrible politically incorrect joke with my word problem. I'll do better on the test. I'll try to do better to offend at least some political class in here. Let's see here. This one is not bad. And I remember I put the derivative on the board here for you guys to try to help you out. I told you the derivative of 2 to the x is log 2 times 2 to the x, you know? And that's really all you need. See, because once you do that, you get a -1 and then rather a 2x minus 1 in the denominator from the differentiation. If you plug 0 into that, you get -1. Well, that's fine. We can divide by -1. That's not a problem. And the numerator, when you plug in 0 into that, you just get log 3 minus log 2. See, because 3 to the 0 and 2 to the 0, they're just 1. So we get log of 2/3, which is about -0.405, which some of you guys gave to me, which is great. Now, some of you wrote -0.405, but you don't really have supporting work. I don't think I really penalized you so much. I'm just like, hey, yeah, you need to show your work, you know? Okay, enough of that. This one here is type what? 0 over 0. L'Hopital that thing. Product rule. We got tangent plus x secant squared over 3 cosine. Well, 3 cosine, that's wonderful, because that means that when we plug in 0, we just got 3. 3 times cosine of 0, which is 1. 3 times 1, 3. The denominator is 3. The numerator is 0. 0 over 3, not undefined. 0 over 3 is just 0. So, done. So that's not bad. This one here, this one's a little sneaky, because I put two things together. I put on the one hand the limit of inverse tangent of something that's getting huge, right? On the other hand, I gave you a garden variety L'Hopital problem. So you got to divide and conquer here. The inverse tangent limits to pi over 2 because you're taking inverse tangent of something that's getting huge. So the limit of the arctangent when its argument is getting very, very large and positive is pi over 2 by the graph of inverse tangent, which we've talked about before a couple times in here. On the other hand, the other piece is like 0 times infinity, or if you like 0 times minus infinity. I don't really distinguish. And as we discussed, I think it's, man, as far as I know, it's almost always the wrong idea to bring the natural log from where it is. We tried this in class. It didn't work for us. So we need to bring the x downstairs to create a ratio, which L'Hopital's rule applies to. So bringing the x downstairs giving you log x over 1 over x, which then I can L'Hopital. I get this, which simplifies to that, which simplifies to that, which of course is just 0. So the answer is just pi over 2 from the second piece. Yeah.
Does the pi over 2 not change when you use the rule because it's not having a limit used on it?
If I had the pi over 2 term included, I couldn't do L'Hopital's. Because the pattern wouldn't be 0 over 0. It would be 0 over 0 plus something that's going to pi over 2. That's not that's not the indeterminate form that L'Hopital's applies to. So just because part of the expression 0 over 0 that's not enough. L'Hopital's, it has to be the totality of what we're taking the limit of is either type 0 over 0 or infinity over infinity. That's when L'Hopital's applies. So if you got something else, I'm just using limit laws. I'm saying, well, and I'm taking out a logic alone in the sense that when I split the limit up into the limit of x log x plus the limit of the inverse tangent, when I make that step, I'm making an assumption that both of the limits which I've written exist, right? Or if one of them blows up and the other one's finite, there's a theorem that says that the sum of them is infinite. That's another theorem that we use. Like if x log x had worked out to blow up to infinity, I would know that, oh, I've got something that's going to infinity after we resolve the indeterminacy, and then I've got something that's going to pi over 2. Okay, so the totality of that plus that would be going to infinity if that were the case. And that wasn't the case, right? That happened to go to 0, so the net results is it went to pi over 2. But I'm using limit laws, in short. But logically speaking, what I really should do to be more logical is I should say full stop, work out a lemma that the limit as x goes to 0 from the right of x log x is equal to 0, and then say, therefore, by limit laws, this is equal to limit of that plus limit of that, since that, that's pi over 2. But we never do that in here because you guys would get like really annoyed if I started doing lemmas and stuff like that. So I just tell students we're taking out a logical loan, like if you split two limits and one of them's infinity and one of them's minus infinity, you can't do that. That's not a legit application of the limit law. Problem 5. So problem 5 is the place where you actually do need to use the technique because it is indeed an indeterminate power. Some of you were doing indeterminate power stuff for other problems, like I said. And so like here, we use the usual trick, exponential of the limit of the natural log of the expression, but 1 over x pulls down from properties of logs. So I've got the star limit, which actually works out to minus 1 by L'Hopital's rule. And then I plug it back in, so the answer is what? 1 over e. So there's that. Let's see here. What else do we have to look at? There is, of course, homework, right? So which homework has happened since the last test? Mission 6, right? Anything in here particular that you guys like to talk about in our remaining couple minutes? What does it mean to verify the theorem? It means check that the hypothesis hold and then actually find the the value which is the claim of the theorem. Like let's look at 240. Let's try to look at 240. Yeah? No? Okay. So verify the mean value theorem for this cubic function on 0 to 2. So I think my solution's actually missing a sentence. Technically, my solution should say, hey, f is continuous on 0 to 2, and it's differentiable on the open interval 0 to 2. So we're looking for, so the mean value theorem applies, right? It's met the preconditions. But this is the meat of it. Like when you're asked to verify the theorem, mostly we're interested in you verifying the conclusion of the theorem, truth be told. So the conclusion of the theorem, the claim of the mean value theorem, is that there exists a constant from 0 to 2, somewhere in there, such that the derivative at the constant is equal to the average rate of change, the average change in y over change in x for the function, which is f of 2 minus f of 0 over 2 minus 0. Now that works out to 1 here, I think. Like 8 minus 6 minus 1 is 1. So f of 2 minus f of 0 is 1. And what? Dude. Aw, man. For true? Oh, wait a minute, f of 0. I forgot to subtract my f of 0. That adds 1. So 2 over 2 is 1. We're okay. This worked out to 1 is what I was getting in my head, but I forgot about this. That's also 1. So 1 plus 1 is 2. 2 over 2, 1. And then we're looking for where the derivative is 1, so we work it out, and there it is. you might not have got this homework problem, right? So I would, I personally, as a student, had a very bad habit. I would study the things I already knew, because it feels good, right? It doesn't feel good to study the part you don't know, but that's the part you probably should be focusing on, isn't it? Yeah, so like if you didn't understand problem 243, maybe you should be looking at problem 243. If you didn't understand problem 249, maybe you should be studying problem 249, right? I have put this question on final, maybe a final, I don't know, but certainly it has been on tests before. And there is like old tests to look at on the website if you want to look there. But anyway, I think that's all I got for today. So enjoy your day off tomorrow. Woohoo! I'll see you guys Thursday.